Howdy. Before we introduce ourselves, we would like to thank the ARP organizers for organizing this expo virtually and giving undergraduate students a much needed opportunity to get a first-hand experience to present our research work. We are a team of 4 students along with a mentor and an advisor. We started this project in spring 2020 with an objective to gain fundamental understanding of metal additive manufacturing. Throughout this presentation, we explain different AM processes, SLM process characteristics, mechanical physical performance comparisons, as well as demonstrate material characterization via digital image correlation technique. Here's an outline for our presentation. What is traditional manufacturing? During the Industrial Revolution, the way items were being built gradually started to convert from hand-built items to more modernized machine-built. It is seen in everyday use, for example, welding, casting, and other similar techniques. It is beneficial for producers because parts can be mass-produced and it allows for people to specialize in certain technical skills. Some downsides are that it consists of longer productivity times, has an excessive amount of waste, and has a limited amount of geometrical capabilities. Additive manufacturing, also known as 3D printing, uses computer-aided design to build objects layer by layer. This contrasts with traditional manufacturing, which cuts, drills, and grinds away unwanted excess from a solid piece of material, often metal. Additive manufacturing consists of 7 different categories that each have a specific range of materials allowable for use, as well as its own set of parameters that make every process operate differently. Some parameters are heat source, orientation of part, and thickness of layers. Additive manufacturing is used in most fields due to the wide range of usage. It can be used to make prototypes, medical components, and common everyday items.
Selective laser melting is a process of powder bed fusion which must occur in an enclosed chamber filled with inert gas to melt either aluminum or metal alloy powders. This process uses a variation of laser beams to melt the material within the chamber. A model must first be created in a computer-aided design software, which then will be sent to be printed in an SLM machine. SLM is widely seen in industries such as aerospace, automotive, consumer goods, and the medical field. The video illustrates how parts are being made through selective laser melting. SLM process parameters are those variables that are involved with the fabrication of metal parts. There are over 100 process parameters involved in the method of selective laser melting. There are 4 major categories that SLM process parameters can be broken down into. The powder you observed in the last slide has many variables that are involved in fabrication of parts through SLM. Variables like the powder size, will the powder flow well, will the powder metal fill up the fabrication area well, and many more questions must be asked. Process parameters associated with the laser can either produce a high density part or produce holes in porosity. Although there are many process parameters, perfecting those can produce parts that are specified to applications and produced through a lean process.
Now, what happens when you compare a traditional part with an SLM part? The following table shows the hardness and tensile values of stainless steel 316 made by SLM and by traditional manufacturing. From the table, it can be concluded that SLM has the higher values. This is due to having fine subgrain microstructure from high solidification or cooling rates at which dislocations form at these boundaries, as well as from high anisotropy at the melt pool boundaries between each layer, meaning the molecules are arranged in different directions, causing variations in physical properties. Lastly, having ideal energy density affects the material's properties, which are dependent on the process parameters. Focusing on the tensile strength of SLM stainless steel, the video shows a tensile test along with a stress strain curve. The purpose of this curve is to show the reaction of a material when a load is applied, and different regions of the curve provides information about the mechanical properties. SLM has a higher curve, meaning it takes more force to fracture the part. The bottom left are SEM images of a fractured tensile sample. It can be seen that it is a ductile fracture because it looks like a cone-shaped tip, indicating there is resistance to the force, and as a result, dimples were formed. To the right are SEM fractographs of the same sample. It shows many defects such as pores and unmelted particles. These defects cause the material to be stronger. Traditional manufactured tensile samples have similar images, but SLM displays larger and more subgrains, pores, and dimples, therefore being stronger than traditional.
Based on previous slides, we then learned a new technique called digital image correlation. DIC is a non-contact optical technique that measures strain and displacement. Compared to the conventional measurement tool, DIC is a non-contact measurement and easy to set up. It also has high accuracy. The figure in the middle represents 2D DIC setup. There are mainly 3 steps for performing DIC. First, apply specular markers, then the camera takes multiple shots of image during deformation. In the end, the software will analyze the image to compute displacement and strains. And the figure on the right is a DIC strain field overlay on a compound bowl. Then we learned 2 of the DIC analysis tools, which are Encore and Encore Post. Encore is an open source 2D DIC program. It uses many novel 2D DIC algorithms, and it is contained within the MATLAB environment. Encore Post is a post-processing application designed for processing, visualization, and export of the data. Figure in the middle is the normal strain in the y direction plot based on the high strain sample provided by Encore. The video on the right shows the color changes which represent the visualization for the strain changes. In conclusion, this presentation begins with the fundamentals of metal AM processes. Then it moved to SLM concept, process characteristics, mechanical, physical performance comparisons. In the end, it demonstrated material characterization via DIC technique. That's it for our presentation. Thank you for listening.